everyone. I'm thrilled to give a flash talk on our recently published paper, Following Carbon Condensation by In-situ TEM, towards a rational understanding of the processes in the synthesis of nitrogen-doped carbonaceous materials. Our findings obtained using in-situ heating TEM have not only given us a better understanding of this complex process, but they have also allowed us to synthesize new materials with enhanced CO2 absorption properties. Now, I would like to take you on a journey through our research. Mitigating climate change starts with efficient CO2 capture. Materials used for this purpose have to fulfill a number of criteria, such as high CO2 uptake and selectivity, low price, reusability, and sustainability. Carbon-based materials satisfy most of the criteria. However, carbon materials often demonstrate lower uptake and selectivity compared to MOFs and cellulites. This issue can be easily overcome by introducing nitrogen into the structure. Nitrogen changes the electron density distribution within the carbonaceous networks and creates basic sites for CO2 capture. A straightforward way to obtain nitrogen-containing carbonaceous materials is through the condensation of a molecular precursor, which already has a high nitrogen content. In our study, we used uric acid as a model molecular precursor. Cross-linking occurs randomly and sometimes poorly for most of the molecular precursors. Therefore, we have amorphous, porous carbonaceous networks as a result. And moreover, the process of cross-linking is accompanied by the porosity formation. Therefore, designing the carbonaceous materials is more challenging than for crystalline ones. Because of this gap in the fundamental understanding of the condensation process, the choice of the synthesis conditions remains rather empirical. And we aim to close this gap. First, by studying the structure and morphology of the condensates ex-situ, and second, by following the condensation process down to the nanoscale using in-situ heating. First, let me strengthen our motivation for in-situ analysis by starting with the Ex-situ study of the material synthesized in inert nitrogen atmosphere at atmospheric pressure, which is the most commonly applied procedure. Before the condensation of uric acid in the nitrogen atmosphere by heat treating it at 500 and 700 and 800 degrees, with a heating rate of 1 degree per minute. In the names of the samples, uric acid, UA stands for uric acid, followed by the temperature, and then the atmosphere and the heating rate. So first, we analyzed the pore structure and CO2 absorption capability of the obtained materials by performing physiosorption experiments. You can find detailed description of the isotherms in the paper, but here I would like to highlight the general trends. An increase in nitrogen uptake of the sample synthesized at 700 and 800 degrees suggests that upon increasing the condensation temperature, porosity develops. Interestingly, despite similar absorption properties of the 700 and 800 materials, there is a very huge difference in their CO2 uptake. At 800 degrees, it decreases in 2 times. The reason for that might be a lower nitrogen content of the 800 sample. Indeed, the nitrogen content drops significantly when heating from 700 to 800 degrees, as you can see from the carbon to nitrogen ratio. Next, we aim to understand if the difference in CO2 uptake arises solely from the difference in the pore structure and nitrogen content, or if there is different ordering in the short-range order of the materials. To study the short-range order, we performed pay distribution function analysis. As you can see, the materials are indeed amorphous, corroborated by TEM observations. And on pay distribution function, you can see that the signal extends only up to 7 angstrom, also confirming the lack of any crystalline order. The only significant difference can be found in their short-range order in the position of the first peak. The first peak for the sample synthesized at lower temperatures at 500 and 700 degrees is located at 1.36 angstrom, and for higher temperature counterpart at 800 degrees, it's located at 1.43 angstrom. So as we were as we could see, the short-range order does not define the absorption properties of the materials. However, the main difference was found to be in morphology of the obtained materials. We used simultaneously secondary electron detector and bright field detector to analyze the external morphology and the internal structure of the samples. These two signals reveal the main difference of the samples, which is the formation of the core shell structure with a different structure of the shell. In the case of 500 degrees sample, the shell is tightly attached to the core, which makes it not accessible for nitrogen during the adsorption. In the case of 700 sample, the shell partly detaches from the core and ruptures on some of the particles, facilitating the access of nitrogen to the core. Therefore, the development of favorable porosity at low condensation temperatures is obscured because of the formation of the core shell structure. To overcome this limitation, we needed to answer two questions. What is the origin of this core shell structure, and how does porosity develop during the condensation? Therefore, we performed for the first time in-situ study of the molecular and not polymeric precursor. Performing in-situ experiment was possible thanks to in-situ heating holder fusion select and heating E-chips from protochips. Similar to Ex-situ study, we used a combination of secondary electron and bright field imaging to follow both inner and outer structure of the particles. Once the temperature reached 250 degrees, we observed the first changes. Based on the secondary electron detector, particles started appearing porous on the surface. Continuing imaging at 250 degrees, at higher magnifications, we noticed slight shrinking and gradual release of matter from the near surface part of the particle, while overall the shape of the particle was kept. After 4 minutes, the particle also started to change inside, becoming more emptied, while no further mass loss was detected. After 64 minutes, the whole particle looks empty. So to sum up the observations at 250 degrees, we could see the first mass release, which indicates the start of the condensation process, and it at the same time is accompanied by the porosity formation and starts already at such a lower temperature compared to the nitrogen atmosphere. Upon further heating to 425 degrees, sintering of the particle occurs, and it becomes more dense due to the redistribution of the pore volume. And the second mass release occurs also at this temperature. And this time it occurs through bubble formation, which coalesce and then escape from the particle, forming a porous network. This process can be assigned to thermolysis. Among the detected processes, the most important is the early stage of the condensation, as it defines the porosity development of the materials. Because of the heat transfer, the surface of the particle has a slightly higher temperature than the bulk. Therefore, the condensation process and release of gases occur first on the surface of the particle. And due to the lower pressure in the TEM vacuum, the release of gases is facilitated, leading to the formation of mesoporous surface, different from the nitrogen atmosphere. Moreover, condensation occurs at lower temperatures compared to nitrogen atmosphere, which is indeed helpful if we want to reduce the energy consumption. Indeed, we can see that the pressure during the synthesis plays a pivotal role in the porosity development. At higher pressures, when the release of volatiles from the surface is partially suppressed, the surface of the particle becomes microporous, restricting further porosity development. Therefore, using these insights from in-situ and ex-situ observations, we performed synthesis of materials in vacuum oven, which, as expected, led to the formation of the particles with mesoporous surface. The condensation in vacuum occurred also at lower temperatures, and already at 500 degrees led to the formation of the hierarchical porosity and 2 times higher CO2 uptake compared to nitrogen samples. As emphasized before, strategy of obtaining carbonaceous materials with enhanced CO2 absorption is to maintain both high nitrogen content and develop porous structure. And while in nitrogen, to develop the porosity, we needed to increase the temperature, which in turn led to decrease in nitrogen content. When using vacuum, we don't have such an issue. And we are able to keep high nitrogen content and already at lower temperature have developed a hierarchical porosity. Not only high CO2 uptake, but also high selectivity of CO2 capture and strength of binding are crucial to obtain a superior CO2 adsorbents. We found that selectivity can be improved by using high heating rates. In our case, it's 10 degrees per minute. And also that the strength of binding for the sample synthesized in vacuum are much higher. So as a result, we were able to follow for the first time the condensation process of molecular precursor at the nanoscale, and also we could show how one can control and tune the formation of pores in nitrogen-containing carbonaceous materials, which we realized by varying pressures and heating rate. Since these parameters change how the porosity of the surface develops and how further it affects the release of gases through the surface and bulk of the particles. And if we use lower pressures, the cross-linking of the molecules is accompanied by easy release of gases, leading to the formation of mesoporous surface. As a result, formed condensates develop hierarchical pore structure on both surface and bulk of the particles, making the entire particle volume accessible for gases during absorption. Using high heating rates allowed us to preserve selectivity of the materials and also to keep a high strength of binding. We believe that these findings provide fundamental insights into the condensation process, which can be applied to a broad range of molecular precursors, giving a new perspective on the design of new materials. With that, I would like to thank you for your attention and also electron microscopy group at the Max Planck Institute of Colloids and Interfaces. And thanks a lot to Protochips for inviting me for this flash talk. Thank you.